Bismillahirrahmanirrahim. Assalamu alaikum. My name is Amul Suhail and my roll number is 21TE04. So today I will be discussing Lab 2 of Digital Signal Processing, which is about signal representation in MATLAB. The objective of this lab is to plot basic signals in MATLAB. So starting with the task 1 of Dsp Lab 2, it is about generating the step signal by entering the starting point and the limits. So let us observe the code. Here we can see the CLC command is used to clear the command window. The close all command is used to close all the existing figures in MATLAB. And N naught is basically used for the starting index of the signal. And N1 and N2 specifies the range of the x-axis. Then N is equals to N1 colon N2 represents or creates an array within the specified indexes, and x is equals to n minus n naught greater than equals to 0, it generates the value 1 for the signal if it is greater than or equal to -1, and it is 1 and it is 0 otherwise. The stem command is used to plot the discrete spectrum or discrete values of the signal. So let us observe the output of this code. Here we can see that the step signal is basically the signal which starts from 0 and move towards infinity, whereas this signal starts from -1 because this is the shifted unit step signal. As you can see, the starting index is n naught is equals to -1, so our output starts from, or our step signal starts from -1 and ranges towards infinity. Here is the task 2 of Digital Signal Processing Lab 2, and it is about generating an impulse signal. As we know that impulse signal only exists at the index 0. So let us observe the code. N naught is equals to 1 is the index at which the shifted impulse exists. N1 and N2 represents the starting and ending indexes of the x-axis, and N is equals to N1 colon N2. This line represents the discrete values within the specified range, and x is equals to n minus n naught is equals to 0, where each element is 1 if the corresponding index is equal to the specified shift n naught, which is equals to 1, and 0 otherwise. The stem function is basically used to generate a discrete impulse signal at the index 1. So let us observe the output of this code. Here we can see that the shifted impulse signal exists at the index 1. Task 3 of this lab is to write a MATLAB code to simulate the exponential signal and the sinusoidal signal. So for the exponential signal, the ranges are specified from -3 to 3, and for the sinusoidal signal, the ranges are specified from -10 to 11, and the exponential signal is plotted using stem function for the discrete values, and for the sinusoidal signal, we have to use the cos function to plot the signal, and stem function is used to plot the values of the cosine function in discrete domain. So the output of this code is there are two figures generated. The first one is the decaying exponential signal, and the second one is the cosine function. Task 4 is to write a function to simulate unit impulse sequence. This MATLAB code creates a function named unit impulse, which generates a unit impulse signal based on the input indexes n. It initializes an output signal y as a 0 vector and then sets the values in the y to 1, where the corresponding indexes in the input vector n are equal to 0, and creating a unit impulse at the origin. The function utilizes a stem command to plot the generated impulse signal, where the x-axis represent the indexes n and y-axis represent the y vector. This results in a concise and visually intuitive representation of unit impulse signal centered at the specified origin, which is 0. So let us call the function of unit impulse. Here we can see that this unit impulse signal is represented which exists at the index 0. The next task is to write a MATLAB function to simulate unit step sequence. This MATLAB code creates a unit step function to generate a unit step signal by initializing an output signal y as a 0 vector and setting its elements to 1, where the corresponding indexes in the input vector are non-negative. The stem command is used to represent the signal in the discrete domain. So let us call the function. Here we can observe that the unit step signal exists for 0 and the positive values, whereas it is 0 for the negative values. Task 6 of the lab is to find a signal named x of n by using functions of task 4 and task 5, which are generated for unit impulse signal and unit step signal. So in this code, n is equals to -3 to 3 creates an array n representing the discrete indexes from -3 to 3. X is equals to unit step of n minus 3 is direct unit impulse of n minus 1 defines the signal x of n as the difference between unit step signal and 3 times unit impulse signal shifted at -1. Now let us observe the output. Here is the output of this code, which generates a unit step signal -3 times a shifted unit impulse signal. Here is the task 6b, which includes the statement n is equals to -3 to 3. It creates an array n representing the discrete indexes from -3 to 3. X is equals to 3 is direct unit step, n minus 3 unit impulse, n minus 2 plus unit step minus n represents the signal statement, which defines the signal x of n as the sum of 3 components. A scaled unit step function which with an amplitude of 3 starting from n is equals to 3, a shifted unit impulse signal at n is equals to 2, and a reflected unit step signal about the origin. Let us observe the output. Here is the required output, which is generated after implementing the specified x of n signal. Task 7 of the lab is to write a MATLAB program that can able to flip the given signal. This MATLAB code operates on a given signal, which is original signal. The code first flips the original signal using the flip function and then generates a new signal called the flipped signal. It then displays original signal and flipped signal in the command window using the Dsp function. The original signal is 1, 2, 3, 4, 5, whereas the flipped signal is totally the reverse form of the original signal, which is 5, 4, 3, 2, 1. It also creates a subplot with two stem plots to visually compare the original and flipped plots. The first subplot displays the original signal using a blue stem plot, while the second subplot displays the flipped signal using a green stem plot. As we can see, in the original signal, the highest amplitude exists at the index 5, whereas in the flipped signal, the lowest amplitude exists at the index 5. This means that the signal is totally flipped within the specified range. Task 8 of the lab is to write a MATLAB program that can able to perform index scaling on the given signal. Now let us see the code. This MATLAB code demonstrates index scaling on a given signal, which is original signal. The signal is initially defined as 1, 2, 3, 4, 5. The code then introduces a scaling factor of 3. Now, the index scaling is performed by multiplying the original signal by the scaling factor, resulting in a new signal, which is scaled signal. Then, the Dsp function is used to display original signal and scaled signal in the command window. The original signal is 1, 2, 3, 4, 5, whereas by multiplying the scaling factor with each element of the original signal, we can obtain a scaled signal, which is 3, 6, 9, 12, and 15. This code creates a subplot with two stem plots to visually compare the original and scaled signals. Let us see the plots. The first subplot displays the original signal using a blue stem plot, and the second subplot displays the scaled signal using a red stem plot. Here we can see that the maximum amplitude of the index 5 is 5 here, whereas the maximum amplitude of the scaled signal has reached the value 15 in the scaled signal. By performing the scaling by multiplying each of the element of the original signal by a scaling factor 3, we have obtained the scaled signal. Task 9 of the lab is to write a program that can able to shift the given signal. This MATLAB code generates and visually compares an impulse signal and its time-shifted version. Let us see the output. The first subplot displays a blue stem plot representing the original impulse signal with a unit amplitude at the origin. The second subplot illustrates the time-shifted version where the impulse signal is shifted 2 units to the left, shown in red. Here we can see that the signal is 1 at the index 0, whereas in the shifted impulse signal, the unit impulse signal is shifted at the index -2. Task 10 of the lab is to write a MATLAB program to simulate zero-order hold. Zero-order hold is a method of signal interpolation in digital signal processing. It is commonly used in digital to analog conversion and signal reconstruction. This MATLAB code simulates a zero-order hold operation on a given signal. The original signal is defined with time instants, original time with their corresponding amplitudes, original signal. The code then defines a new set of time instants, hold time with a sampling interval of 0.5. Using interp1 function, it performs zero-order hold simulation, creating a signal ZOH_signal by interpolating the original signal values at specified hold time instants with previous method and extrapolating beyond the original time range. The code displays both the original and simulated signal plots in 3 subplots. Let us observe the plots. The first subplot shows the original signal with the blue markers. The second subplot illustrates a zero-order hold simulated signal with a red step plot. And the third subplot overlays both the signals for comparison. The plots include appropriate labels, titles, and grid lines, providing a clear visual representation of the zero-order hold simulation and the recovered signal. The last task of this lab is to write a MATLAB program to simulate first-order hold. First-order hold is a signal interpolation method that assumes a linear relationship between consecutive samples. Instead of holding a constant value like zero-order hold, it connects adjacent samples with linear ramps, resulting in a piecewise linear approximation of continuous signal. First-order hold is often employed in applications such as digital to analog conversion and signal reconstruction. So let us see the code. This MATLAB code demonstrates the implementation of the first-order hold interpolation technique on a given signal. The original signal is defined by time instants, original time, and corresponding signal values, original signal. The code then defines a new set of time instants for the first-order hold simulation, hold time, with a smaller sampling interval of 0.2. Using the interp1 function with the linear interpolation method and extrapolation, it performs the first order hold simulation, creating a signal FOH signal. The rest of the commands are used to plot different signals on the same figure. Let us see the plots. This subplot displays the original signal. The blue stems represent the original signal's discrete values at specified time instants. The next subplot shows first order hold simulated signal. This illustrates the simulated signal using first order hold interpolation. The red line represents the piecewise linear approximation of continuous signal between the specified hold times, whereas the third subplot overlays the original signal with blue stems and the first order hold simulated signal with red line. It provides a visual comparison between original discrete signal and its interpolated version. Both signals are plotted together for a comprehensive view, and the plot includes appropriate labels, titles, and grid lines for clarity. Thank you so much for watching. See you in the next video. Allah Hafiz.